So I want to go through some examples, but before we get to the examples, I do want to stress kind of the big picture. And the big picture here is that the first thing that we want to know about any variable that we're gathering is what type of variable it is. And again, that's that scale that basically a nominal scale is name only, it's categorical data. An ordinal scale means that the numbers have magnitude, but we don't necessarily know the difference between each number. So first, second, and third, we know someone that first is better than second and second's better than third, but we really have no information about the distance between how well first did versus second versus third. And what we want is basically that continuous or interval scale, where again, the numbers have meaning, they have magnitude, but they also have near or close to equal interval. And finally, if we can get ratio data, we want ratio data, and that simply means that the scale is no longer arbitrary. It starts at 0, and 0 means 0. Now, again, when we're talking about these measures of central tendency, when we're talking about especially mean and standard deviation, the types of scales we're talking about, the type of measures we're talking about, are either going to be interval, which have name, magnitude, and equal interval, or going to be ratio. Name, magnitude, equal interval, and 0 is an absolute value. 0 means 0. So just keep that in mind. And then once we have one of these continuous variables, we can use mean and standard deviation as a descriptive way to summarize all that data, assuming it's in a normal distribution. So I just want to go through a few examples right now of kind of both what we gather, what we can know, and what we cannot know by using these summaries, if you will, these descriptive statistics of larger data sets. So my first example is going to be quiz grades. So Dr. Popper has finally posted the Pop Score quizzes. There was 5 questions worth 9 points each, so possible scores range from 0 to 45. So again, 0 means you got 0 right, and 45 means you got all 5 questions right. So self-quiz yourself here right now. What type of scale is this? Is this a nominal scale? The numbers are only labels. Is this an ordinal scale? The numbers are labels, but they also at least have magnitude. Is it an equal interval scale? So do we have actual equal interval magnitude and nominal? And finally, ask yourself, does 0 actually mean 0? So is it a ratio scale? So which type of scale is this? Hopefully you said ratio, and that is correct. This is actually a ratio scale because the 0 truly represents 0 of something, 0 to 45. So Kelly, who took this quiz, found her score quickly, and it was a 32. So 32 out of 45. Now again, think about, if you got a 32 on this test, what would you think about that score from 0 to 45 points? Now, the first thing you might notice is that means that these questions were not all or nothing. In other words, 32 does not divide by 9. That means you could get partial credit. So Kelly's got a 32, which is above the center point. So if we took the center of 0 to 45 to figure out basically what's a 50%, that'd be a 22.5. So we know she did at least better than a failing grade. And she may feel okay about this score. 32 is not great, but it's better than nothing, and it certainly deems a little bit better than failing. But if we really wanted to know how well Kelly did, we'd need to know more about the actual scores, not just what range it was on. So again, how do you think Kelly feels about this score, and why would you think that? And again, with the absence of descriptive statistics, the only thing we can compare Kelly's score to is the possible scores. So we don't know if anyone got a 0. We don't know if anyone got a 45. We don't know what the most common answers were, or common point values. We don't know what the range was. All we know is the scale, 0 to 45, and that Kelly has a 32. Now, if we had access to the raw data, we could probably start picking through all that raw data, figuring out how many people scored below Kelly, how many scored above them, what was the lowest score, what was the highest score. But that's a lot of work, and we want to be able to figure that out quickly, and that's where those descriptive statistics are going to come in again. So Dr. Popper posts some descriptive statistics of this score. These statistics describe the scores in the pop quiz. The N was 50, so 50 people took the test. The mean was a 38. So the mathematical center of the scores was 38. If you added all 50 scores together and divided by 50, the number that came out was 38, which means half the population, in this case 50, so approximately 25 people scored above a 38, or 38 or above, and 25 people scored a 38 or below. The median is a 40. So again, this starts to tell us something. This tells us it was not perfectly normally distributed. And in fact, at that point, it looks like there actually may have been a little negative skew, dragging the mean to a lower number than the actual most common responses. Remember, median is we put all 50 scores in order from the lowest to the highest and then found the midpoint. And in this case, the midpoint number, and this was an even distribution, so 50, that means there was two numbers. They were probably either 42 and 38, averaged of 40, or maybe both of them were 40. 40 plus 40 divided by 2 is 40. So the median was 40. This doesn't tell us that this was definitely a strongly skewed distribution, but it does tell us that there was probably one or two lower scores that was dragging that mean away from the midpoint. The mode, the most common response, was a 44. So the most common score on this test, which ranged from 0 to 45, was a 44. The median, so the average of putting them all in order and finding the midpoint, was a 40. The mathematical average was a 38. Now with this data, we can start to tell that basically most scores were above the mean. The mean's being dragged downward to a lower score. Now that starts to make some information that we can use, because we now know also that basically, assuming it was a normal distribution, and it sounds like it was a little skewed from this data, but assuming it is a normal distribution, the standard deviation was 8.02. We'll round that to 8, which means that if it was a true normal distribution, basically, not only is a 38 the midpoint, that would mean that a 46, which is actually above what you can score, would be the top half of that standard deviation, and down to a 30 would be the second. So that would basically tell us that about 65, 66% of the population would score between a 30 and a 46. That also means there's a fair amount of distribution here, because the standard deviation is actually kind of exceeding the scale. And this kind of, again, tells us that not necessarily do we know exactly what this distribution looks like, but it does start to give us some information that it isn't necessarily a normally distributed sample. Now at this point, we have to come back to how do you think Kelly feels about her score of 32 now? So even if we can trust that lowered mean of 38, she's still 6 points below the average, which means more than half the students did better than her. And we also know that from the median and the mode, that most people actually were probably scoring even above that mean more so. So that 32 starts to sound a lot less positive than it did before we had these descriptive statistics. So if we actually look at the distribution, we can see indeed this is not a normal distribution. That if we actually look at the count, about 12 or 13 people got a perfect score of 45, and 20 people got a 40. 35 was about 5 or 6 people, and that 32 falls into only a few people got it. And notice that there was one person that got a 0. And then another person that got a 20, then a 25. So again, we see that mean is being dragged towards that 0 point, that outlier, that extreme score, which means that we can use that information a little bit less. I really hope that you're kind of getting a feel for why we use descriptive statistics, to try to give a lot of information with only a few numbers, but also the danger of using descriptive statistics if that distribution is not normally distributed. So let me use one last example, and really this example, I'll tell you right ahead of time, there's a little bit of a trick here, and this example is basically illustrating kind of the limitations of descriptive statistics. So not only are we worried a little bit about how we represent mean and standard deviation and making sure we're only representing it when we have a normal distribution of continuous data, and again, continuous data is kind of a catch-all term that means that our scale is either interval or ratio. So Dr. I.M. Vane wants to know how physical attractiveness influences attraction. Dr. Vane shows male college students a photo either depicting a physically attractive female or a less physically attractive female. So again, there's a manipulation here. Dr. Vane is randomly determining whether each participant is going to see one picture or the other. After they see the picture, he asks the students to report how attracted they are to that female shown in the picture. So he gets some demographics of his sample. So the mean age, so age is ratio again. 0 means you have 0 years. 15 means you have 15 years. So the mean age was 20.5 with a standard deviation of 3.1. So again, that tells us if it was normally distributed, that about 68% of our population fell between 17 and 23 approximately, and most of the population was probably between 16 and 26. Now again, if this is a college sample, that's probably fairly skewed data. You probably don't have anyone under 18, and it's probably a few non-traditional students in their 30s and 40s kind of dragging that number over. The gender is 100% male. That was one of the requirements of the study. Looks at ethnicity. Now again, ethnicity is just labels. There is no magnitude here. You really can't talk about midpoints. It would be inappropriate to talk about mean and standard deviation on a scale of ethnicity. You're simply talking about percentages. What was the percentage of people that reported each of the ethnic conditions? Income, again, is a ratio scale. You can make 0 money all the way up to making hundreds of thousands of dollars. And again, the income of the sample was an average of $7,123.5 with a standard deviation of about $4,000. And again, you can see from that standard deviation, there's probably some extreme scores in there as well. Most college students are probably making a relatively small amount of money, but there probably was a few non-traditional students holding jobs that dragged that number up. And finally, what class they were in. Again, that's a categorical piece of information. It'd be inappropriate to report mean or standard deviation. And in fact, even mode is not telling you much. So for example, I'll ask you now, and see if you can figure this out. If you were simply reporting the mode, what would be the mode of ethnicity and what would be the mode of class? I'll give you a few seconds to think about that. Remember, mode is the most common response. So yes, ethnicity, the mode would be white. But that doesn't tell us much because we probably want to know what percentage of people were white, what percentage were black, Hispanic, Asian, and other. And likewise for class, the mode would be junior. That was the most common response. But again, we're probably interested in finding out all of the categories. So usually, again, I kind of talked about that mode is rarely used. That's because usually it's more important to simply list the percentages of each category. So the attraction scale in here is a Likert-like scale going from 1 to 7, with 1 not attractive at all and 7 being extremely attractive. And again, every participant rates the picture that they see on this scale. Here is what Dr. Vane found. And what does these descriptive statistics tell us about the influence of physical attractiveness on attraction? So he had 72 total population. So 72 people, not population, sorry, sample. So his sample that he hopes to generalize back to the population with was 72 males that came into his study. He finds that the mode, most common response, was 2, the median is 4, and the mean is 4.1. Now again, we see that there's a little bit of an issue here. We want to see the mean, the median, and the mode to be pretty much close to being the same number. So the mode tells us there's probably something a little bit weird going on with this data set. We still haven't actually looked at the distribution though, so we also calculate the standard deviation if we can use it. So again, the mean is 4.01, we'll just round that to 4, and the standard deviation is 1.84. So again, about 68% of the population answered somewhere between basically a little above 2 to a little below 6, the mean plus or minus standard deviation of 1.84. And here's what the data actually looks like, and you can tell this does not look like a normal distribution. So again, we have the frequency attraction. Remember, our mode was 2, so you can see that 2 was a very common response, but 4 was almost as common, and some people put 7. And this is the kind of trick question, if you will. What we're doing here is, remember, there was a manipulation. In other words, descriptive statistics of the outcome, the measure of attractiveness, is unlikely to be normally distributed because we did something to change that score in one group versus the other group. So this is basically a graph that's showing us both the people that saw the less attractive picture and those that saw the more attractive picture. And what would be much more honest is what we want to look at is the difference between these two groups. So if we separate out the students that saw the attractive versus less attractive, we see that each group was exposed, so basically half. 36 saw the attractive photo, 36 saw the less attractive photo. And again, that's represented by N. What was the N of these subsets of that sample? And we can see the mean difference. So let's look at the attractive sample. We have a mean of 4.97. We have a median of 5.0. That's looking good. But we have a mode of 4 and 7, bimodal. That basically tells us it's very unlikely this is going to be a normal distribution. So some people found the attractive photo to be very attractive, but an equal number found it to be just moderately attractive. We've got the standard deviation there, but honestly, we probably can't trust that number very well in this particular distribution. In other words, something kind of weird was going on. There's probably some variable that we missed that we should have been measuring. It might have been that people that were in a relationship saw the attractive photo as a 4 because they didn't find them that attractive because they were already in a relationship. While the people that were in a relation or not in a relationship found the picture to be more attractive because they were actively looking for a partner and rated it a 7. We just don't know what's going on, but we can tell something's going on because if there wasn't anything else affecting those ratings, we probably would have expected to see a more normal distribution. If we look at the less attractive condition, also with 36 participants, we see a mean of 3.06, cool. We see a median of 3.0, not bad, and a mode of 2. And again, that represents probably this distribution is a little more normal, but again, we've got some sign that we have a positive skew here. In other words, the mode, the most common response was a 2, but the mathematical average was larger than that. And again, if we could trust that standard deviation, we calculated that as well. So if we look at this now from that split, this is what we actually find. Then the less attractive condition, indeed, it's a little bit more of a normal distribution. It's a little sharply curved there, but we definitely have that positive skew of the people that even in the less attractive condition rated the photo either a 5, 6, or 7. And likewise, in the attractive condition, we actually have a bimodal distribution where about half our population was seeing it as a 4, 3, 4, or 5, but there was a subset that were seen as a 5, 6, or 7. So again, I just really want to kind of use this as an example to say that mean and standard deviation are very useful if we have normal distributions, but we have to make sure it's appropriate. And also, descriptive statistics work best when all we're doing is describing one variable. If we're starting to compare variables, if we're starting to look for differences between groups, we need to basically subdivide those groups before we apply descriptive statistics. Because trying to lump them all into one variable or one category, we're going to find some weird results, and we'd expect to find weird results because we were hoping to find a difference, and now we're capturing all of those differences in one measure. So when we're talking about descriptive statistics, you want to ask yourself, did I do anything to create subgroups? And if I did, I need to run the descriptive statistics on each subgroup individually if I'm really expecting to find out what's going on.